In our final video for the semester, we're just going to go over quickly some properties of integrals. And I already mentioned one in the last slide, or in the last video rather. Okay, so the first property that I want to talk about is that if I'm integrating from a to b of f of x dx, okay, I don't have to integrate all the way from a to b in one piece. If I want to, I can split the integral up into two pieces. So I can say, instead of finding the area under the curve from a to b, I can find the area from A to C, then find the area from C to B, and then add the two pieces together, okay? Remember, the integral is finding the area under the curve. So instead of finding the area in one piece, I can say find the area of this piece, find the area of this piece, and then add the two pieces together, and that will give me the same amount, okay? So this property says I can integrate from A to C, and then integrate from C to B, and this will be equal to the original problem as long as the number C is in between A and B. Okay, so that's the first property. The other property that I wanted to mention is that if the upper limit and lower limits are equal. So suppose in my problem, I have something like this. I'm integrating from A to A of f of x dx. Suppose, for instance, that A is a 2. So suppose it says, find the integral from A to A of f of x dx. Now remember that this represents the area under the curve. So if I'm integrating, and here is my interval, it starts at 2 and it ends at 2. And suppose I have a function, but I'm only looking at the interval from 0 to 2. Do I really have any area under the curve? No, because it's really just a single point, right? There's just a single point there, so there's no area. So if I was to evaluate this, also you can see that to evaluate this, the antiderivative is f of x. If I evaluate it at the upper and lower limits, I would get f of 2 minus f of 2, and the answer would be 0. Okay? So if the upper limit and lower limit are equal to each other, the answer will always be 0. Okay, so that's the second property I wanted to mention. So the integral from a to a of f of x dx is equal to 0. The third property is that if I have an integral from a to b of f of x, and I switch the upper and lower limits of integration, then that's going to give me a minus sign. So in other words, if I integrate from a to b of f of x dx, and now instead, I change the order of the limit. So I switch the upper limit to the bottom limit. What this does is that it makes the answer negative. Okay, so if you switch the upper and lower limits of integration, you're going to get the negative of your answer. And this is also easy to see because, for instance, if you were to evaluate this using the fundamental theorem of calculus, this would come out to be f of b minus f of a. Right? You would find the antiderivative, you would plug in the upper limit first, and then minus the lower limit. In this one, remember I have my minus sign in front. If I was to evaluate using the fundamental theorem of calculus, I would have f of a minus f of b, because I need to plug in the upper limit first and then the lower limit. Now, if I distribute this minus sign in front, it's going to give me minus f of a minus a minus f of b, which is really just f of b minus f of a. Okay? And finally, the last property, which is a very important property, and it's part 2 of the fundamental theorem of calculus. So the first part of the fundamental theorem of calculus tells us that instead of taking the limit of the Riemann sum to find the area under the curve, all we have to do is find the antiderivative. Okay? This is part 2 of the fundamental theorem of calculus. So this property is very important. Suppose that you're integrating, and instead of integrating from a to b, normally when we integrate, our limits of integration are constants. However, suppose this time I replace my upper limit of integration with a variable. So I'm going to replace this with an x. Now I should also point out that here in my formula for my integral, I don't have to call the variable x in the function, right? Because I can use whatever name I want. So if f of x, for instance, is equal to x squared, if I call the function variable t, then the function would be t squared. It's still exactly the same function. I just gave the variable a different symbol. Okay? So in this formula, if this is an x, then I should put a dx. If I want to make this a t, then I have to change this to a t as well. Okay? So I'm just going to use t now because I don't want to use the same variable here as here. Okay, let's look at a picture of what this means. Suppose I have my function. I always go to my function f of x is equal to x squared just because it's easy. Okay, so let's call this function, instead of calling it f of x, let's call it f of t this time. Okay. Normally when we integrate from a to b, where b is a fixed constant. So I'm finding the area under the curve from a to b. This time I'm integrating from a to x, where x is a variable, which means that the value of the right endpoint can change. I can make the right endpoint smaller by moving into the left, or I can make it bigger by moving out to the right. If I was to make x smaller by moving into the left, the answer for the integral is going to get smaller because there is less area. And if I was to move x out, then my answer for the integral is going to get bigger because now there's more area. Okay? In either case, part 2 of the fundamental theorem of calculus now says, suppose I want the derivative of this expression. Okay? Now, first of all, let's evaluate this before we do the next part. Okay? If I was to evaluate this, by the first part of the fundamental theorem of calculus, it says find the antiderivative, which is f of t, and then plug in the upper and lower limits of integration, which is f of x minus f of a. Okay. Part 2 of the fundamental theorem of calculus now says, suppose I want the derivative of this integral. Okay. I want to know the derivative of this integral. But this integral is equal to this. So it would be the equivalent of taking the derivative of this expression. Well, what is the derivative? Remember that the derivative of f of x is lowercase f, because capital F was the antiderivative. So lowercase f is the derivative. Now this is a constant because it doesn't have a variable. Okay? It's the antiderivative evaluated at a, so it's a number. The derivative of a constant is 0, so this part goes away, and the answer is just f of x. Okay? So to simplify this, the fundamental theorem of calculus tells us that if we want the derivative of the integral, where the upper limit of integration is x, the answer is just f of x. In other words, these two things are like opposites, right? You're finding the derivative, but when we evaluate an integral, we're finding an antiderivative. So you're taking the derivative of the antiderivative, which basically cancels each other out, and you just get the function itself. Okay? So this function that was in here, you get that function, except for the variable is now x, because the upper limit is x. So whatever variable is here, that's what you would plug in. Okay? That's the fundamental theorem of calculus, part 2.